podcast is brought to you by LMU Munich.
Speakers and the future ones for thanking the organizers for this conference. It was flawlessly organized, the talks are wonderful, and the trip was great. I would like to report on work done with five co-authors, and the report is reported in these two papers. Okay. So throughout the talk, I'll be primarily in 3 dimensions. I will not say anything, I'll not say about it again, so just remember we are in 3 dimensions, unless said otherwise. And this is the outline of the talk. I'll start by defining Chern-Simons contact terms. In this part of the talk, I will not use supersymmetry. In the second part of the talk, I will extend the discussion or specialize the discussion, depending on your point of view, to supersymmetric theories. And here we will see that there are a number of different supersymmetric Chern-Simons contact terms. They have different properties, and they lead to interesting consequences. One of them is a new kind of anomaly, reminiscent of known ones, but it is new, which appears as a clash between superconformal symmetry and the compactness of U1R symmetry. And this will lead me to a discussion of the partition function on the 3-sphere. This has been a popular subject in the last few years, and I reviewed it in my string talk in Uppsala last year. So I'll say a few words about that, and then I'll present 2 applications of this understanding. One will be a proof and further insight into the conjectured F maximization, and the other application will be new tests of duality, which are analogous but fundamentally different than the 't-Hooft anomaly matching conditions in 4 dimensions. And I'll end with some conclusions. So what are contact terms? So this is field theory 101. Contact terms are correlation functions at coincident points. We have 2 operators, and there could be a delta function or a derivative of a delta function when they are on top of each other. And they're not discussed very much for one simple reason. They are either completely determined or they're completely arbitrary. Examples where they're completely determined are the Siegel term in scalar electrodynamics, with the coupling of 2 photons and 2 scalars. It's a contact term, and it follows for imposing gauge invariance. Another example is the trace of the energy momentum tensor, say in 2-dimensional conformal field theories. Now the trace of the energy momentum tensor is 0 as an operator, but its coincident point correlation functions cannot be 0, and this is known as the conformal anomaly. So the conformal anomaly sets the contact terms of the trace of the energy momentum tensor in order to preserve energy momentum conservation. Now, most contact terms are not like that. They are completely arbitrary. And there are several complementary ways of thinking about it which are fundamentally equivalent. First of all, contact terms clearly reflect short-distance physics. It's not correlation functions at separated points, but when the 2 operators are as short, the distance between them is as short as possible. Second, the values of these contact terms depend on the regularization scheme. If we change the regularization scheme, the values of the contact terms change. Equivalently, we can construct local counterterms either in terms of the fundamental fields or in terms of background fields. And throughout this talk, whenever I see a coupling constant, I'm going to think of it as a background field. So we can add to the Lagrangian local counterterms, and I distinguish counterterms from contact terms. We can add, they are arbitrary, as they reflect short-distance physics. And since they are arbitrary, the corresponding contact terms are arbitrary. And finally, these contact terms can change if we just do field redefinitions, either redefinitions of the dynamical fields or coupling constant, or equivalently background fields redefinitions. So all these different ways are equivalent. These different ways of thinking about it are equivalent, and that's why most of them are arbitrary. I'm now going to present a notable exception, a contact term which does not fall into this discussion. It's neither arbitrary nor determined. And that's it. We study a 3-dimensional theory which has a global U1 symmetry, and let the U1 charges of all the fields be quantized. Then we can think of this U1 as being compact U1. Now, how should we think of the global symmetry? There is a conserved current because of Netter's theorem. So we can couple it first to an infinitesimal, but eventually to a larger background gauge field. So we have a U1 gauge symmetry, sorry, a U1 global symmetry. We have currents, and the conserved currents can have such a contact term. Notice that this contact term is indeed, it's a derivative of a delta function, so it's really very localized. It has a coefficient with 2 pi for convenience. And I'd like to emphasize that even if the theory is conformal, this term is still invariant under conformal symmetry. So this is a perfectly allowed conformal contact term. And equivalently, we can think of it as turning on background gauge field, and at least if the gauge field is infinitesimal, we can add to the Lagrangian such a counter term, a dA. And if we could think of the two-point function of j as taking two derivatives with respect to a, we see that this counter term leads to a delta function proportional to this kappa. So if we just apply the standard contact term dogma, the thing that appeared on the first slide, or you study in Field Theory 101, you would say that there is no interest in this kappa whatsoever. We can change the value of kappa by adding a local counter term. In fact, here it is. We just take the definition of the Lagrangian and add this term, and by doing that, we'll change the value of the contact term. So this is the standard dogma, but here it's imprecise. It's imprecise because we would like to think of this U1 symmetry as being compact, and we would like to think of this background little a as being a gauge field. And now when the gauge fields are not infinitesimal, we have to worry a little bit about the topology. And there are several different ways of saying it. The imprecise way is that we would like the functional integral to be fully gauge invariant under large gauge transformation where the U1 can wind around and there are non-trivial bundles. More precisely, we should think of the Chern-Simons term in terms of a four-dimensional extension of the fields, and then we would like the answer for the Chern-Simons term to be independent of the extension. So I'll abuse the language and I will just say that this is full gauge invariance, but this restricts the allowed values of this contact term, of this counter term. So when we say that we define the theory, we have freedom in changing the counter term, but the freedom is only in adding integers. We are only allowed to add arbitrary integer values. So unlike the general contact terms I mentioned before, the integer part is arbitrary, but the fractional part is physical. So kappa mod 1 is a physical observable. This is a physical observable which characterizes the theory, and it can be measured. And there are examples of that in the Hall effect and various other examples which were published in various three-dimensional theories with different amount of supersymmetry. Now this entire discussion can be repeated for the correlation functions of the energy momentum tensor. There's a similar contact term there associated with the Lorentz Chern-Simons term. Again, in some units, kappa is quantized, the freedom in kappa is quantized, and the fractional value is physical. And I should also emphasize that my normalization here is only for spin manifolds, otherwise there are additional factors of order 1, which I'm not going to get into. The concepts are more important. So now let's take this discussion and supersymmetrize it. When we supersymmetrize it, first we say, let's pretend we didn't notice that the theory is supersymmetric. So we have a bunch of Chern-Simons contact terms, and the fractional part is physical, and the integer part is arbitrary, and it can be changed. However, there are new elements in supersymmetry, because we would like to impose not only gauge invariance, etc., but we would also like to impose supersymmetry. Here the discussion splits. Our global U1 symmetry can either be an ordinary symmetry, which commutes with supersymmetry, or it could be an R symmetry. So let's start with an ordinary symmetry. For an ordinary symmetry, the U1 current is in a multiplet with other fields, and correspondingly it couples to background gauge field, and the U1 gauge field is this little mu, but there are additional scalars, sigma and d, and from fermion lambda alpha. And then the contact terms are associated with such Chern-Simons terms, and we see that the contact term in the two-point function of two currents, which is dictated by the coefficient of a mu by this term, which is quadratic in the gauge field, is correlated by supersymmetry by the contact term in two scalar operators. One couples to sigma and the other couples to d. And similarly, there is a contact term in the two-point function of various fermionic operators. Everything I said so far in the non-supersymmetry case is still true. The fractional part of kappa is physical, and the integer part can be changed. And I would like to emphasize something that will be important soon. This term is still conformally invariant. So if we have a superconformal field theory, we can add this term, and everything we said is still true. Now things are getting a little bit more interesting when we study an R symmetry. An R symmetry does not commute with supersymmetry, and therefore the supersymmetrization of the R current is a little bit more subtle. It involves the energy momentum tensor and a bunch of other operators. In terms of background fields, the U1R gauge field is related to the metric and a bunch of other fields. So the Chern-Simons terms that we're going to write are a little bit different. Let's first pretend that we did not notice our theory is supersymmetric. If we don't know that the theory is supersymmetric, we just make a list of all possible Chern-Simons terms. So we had Chern-Simon term before of 2 non-R symmetries, and now we have to add 3 more terms. The Lorentz Chern-Simons term that I've already discussed, and 2 new ones, a U1R and a flavor symmetry, and an R symmetry and an R symmetry. So that's all we can do. And what appears here, everything we said before is still true. The fractional part is physical, the integer part can be changed. But now we see a new element. In the course of supersymmetrizing this term, we have to add some terms here which are represented by the ellipses. And I did not write them explicitly in order not to clutter the equations. If you're really interested, they're spelled out with all the coefficients in our papers. And the crucial thing about these terms in the ellipses is that these 2 terms are not superconformal. This term is conformal, as it was without supersymmetry. Without supersymmetry, this first term, this one and this one, is conformal, but the terms in the ellipses are not conformal, which means that the 2-point function of, say, an R current and another R current, it's perfectly conformal. Its contact term is conformal, but the supersymmetrization of that relates to terms which are not conformally invariant. It just follows from using naive supersymmetry. And this has interesting consequences. So imagine we have a superconformal field theory. We have a superconformal field theory, we would like to impose some physical requirements on the correlation functions. One, obviously, supersymmetry. The second, conformal invariance. And the dogma is that no anomaly in 3 dimensions, and therefore there shouldn't be any problem in imposing conformal invariance. And the third, that all flavor and R symmetries are compact, all the charges are integers. That's true in the UV, so that should be true after flowing to the IR. If the flavor R and the RR Chern-Simons terms are quantized, no problem, we'll just use the freedom we have to add counter terms to fix the problem. But if it so happens that these contact terms are not quantized, we are in trouble. And I'll show an example of that soon. So what should we do about that? Imagine we are given a superconformal field theory, and these counter terms, these contact terms are not properly quantized. So one approach is just to live with this and say that the contact terms are not conformally invariant. This is very much like the conformal anomaly in 2 dimensions. A more conservative approach is not to sacrifice conformal invariance. More generally, whenever we have an anomaly, we make a list of physical requirements, and for one reason or another, we cannot satisfy all of them, so we have to sacrifice one of them. So we have to sacrifice the one we like the least. And in this case, it's the compactness, the fact that all the flavor and R symmetries are compact. If we sacrifice this for a moment, then we can add fractional Chern-Simons terms with fractional coefficients. We sacrifice something, I'll soon be more specific about that. Now all the contact terms are conformally invariant. So what exactly do we sacrifice? If the gauge fields are infinitesimal and we don't study large gauge transformations, we don't sacrifice anything. The only problem is that if we have certain bundles which are non-trivial and we want invariance under large gauge transformations which wind around it. So that's what I say here. So first of all, oops, this thing doesn't work very well. So that's what we do, and this is similar to Witten's famous framing anomaly. He needed to add a fractionally charged Lorentz Chern-Simons term in order to ensure topological invariance. Here we need to add such a term in order to ensure conformal invariance or superconformal invariance. we'll soon see that this anomaly can become more severe when we proceed further in the talk. And more precisely, the issue is not gauge invariance, but how we extend it to 4 dimensions, but I told you that I would abuse the language and say it's gauge invariance. So this is a legal disclaimer. So here is an example which is good to keep in mind. It's kind of a canonical example. Many people in the audience studied this theory in a lot of detail. This is a U1 gauge theory with the Chern-Simons term for dynamical fields, level K, and it has NF flavors of electrons and positron, or chiral superfields of charge 1 and chiral superfields with charge -1. This theory flows in the infrared to a non-trivial fixed point. It's a conformal field theory, which is labeled by 2 integers, n sub f and k. What do we know about this field theory? We can compute a few things using localizations or perturbation theory, and in particular, we can use a large K expansion, and in perturbation theory, we can compute this contact term. And this is a straightforward but somewhat tedious computation. The 1 over K term is a 2-loop graph. In fact, there are various tricks to do it in 1 loop, but I will not discuss them. And then there are higher order corrections. The important thing to emphasize here is that these numbers are fractions. The contact terms are fractions, so we really find a physical observable. This is not something that can be removed by adding a counterterm. The second thing we see here is that the flavor R and the RR Chern-Simons term, which I did not write here, are non-zero. So we are precisely in this situation where this anomaly I mentioned is present. This theory, as it stands, if I insist that all the U1 symmetries are compact, which is true at short distance, this theory, we cannot preserve this compactness together with conformal invariance. We cannot have both, and we should sacrifice one or the other. And I'll soon tell you what it means. So one way of doing it is to add the appropriate counterterms to violate the invariance under large gauge transformations and have a perfectly good superconformal field theory, including all contact terms being superconformal, or sacrifice superconformal symmetry and preserve invariance under large gauge transformations. The next topic I'm going to talk about is placing these theories on spheres and see how the discussion so far affects the answers. So how can we do that? Well, this was first done by Diptiman Sen in a widely ignored paper in 1984. This is not Ashok, it's somebody else. And was taken on more recently in the 90s by Rombelsberger, but really caught fire with the beautiful work of Kapustin, Willett, and Yakov, and many, many other followers. So they put the theory on a sphere and used localization to compute the partition function and found all sorts of marvelous results. So how should we put the superconformal theory? How should we put the supersymmetric theory on a sphere? Let's start with superconformal theories. This seems to be straightforward. All we need to do is perform a conformal transformation or a stereographic map from R3 to S3. This seems to be completely straightforward. So let's do that. If the theory is non-conformal, it's a little bit more subtle because we cannot just perform this stereographic map. And in the last spring meeting, I reviewed my work with Festuccia. We showed how to do that using background fields. And I emphasized then that we have to sacrifice something else here, and this is to use imaginary background fields. The background fields do not have their standard reality. This actually makes sense. We shouldn't be able to preserve supersymmetry on S3, because if we could have written the theory in de Sitter 3. And everybody knows that in de Sitter 3, there are no supersymmetric theories. In de Sitter space, we cannot preserve supersymmetry. So if we cannot preserve supersymmetry in de Sitter space, we cannot preserve supersymmetry in Euclidean de Sitter space, which is the 3-sphere. The correct statement is actually that we can preserve supersymmetry in de Sitter space if we do not preserve unitarity. So that's the reason of these imaginary parts, which will soon be important. So let's go back to the sphere partition function. Imagine we preserve unitarity. The sphere partition function has to be real. It has to be real even if the theory is not parity invariant. And the argument for that is very simple. For every configuration in the functional integral, there's another configuration obtained by reflecting the original configuration. The two actions of the original and the reflected configurations do not have to be the same. The theory is not parity invariant, they're not the same. But if the theory is unitary, the two contributions should be complex conjugate of each other, and therefore when we add them together, the partition function has to be real. So a unitary field theory must have a real partition function. So this is true in general, but then somebody could ask, what about all these imaginary parts which ruin unitarity? Well, they should be harmless if the theory is conformal, because if the theory is conformal, we don't need to add all these background fields. All we do is just perform a conformal transformation. Okay, so this is the general background. We expect the partition function of a superconformal field theory on S3 to be real. However, explicit computation by various people have led to complex answers. These people computed using localization the sphere partition function on S3, this S3 partition function while preserving supersymmetry, and the answer turned out to be complex. How should we interpret the phase of the partition function? We start again from flat space. This is a general rule about field theory. When you're confused, don't run to complicated manifold, but work on flat space, flat non-compact space. So we start in non-compact space, non-compact flat space, and we study various correlation functions, and among others, we find our 4 supersymmetric contact terms. And the 4 supersymmetric contact terms are calculable in perturbation theory. We find their answer, and they're physical. Now, if we do not add bare counter terms to fix the problem with the offending terms, the ones which are not conformal, then our theory is not really superconformal. It's superconformal at separated points, but it's not superconformal at coincident points. The contact terms of the theory do not respect superconformal theory. And therefore, when we put the theory on the sphere, this lack of conformal invariance through the contact term comes to haunt us, and it leads to a phase in the partition function. We can say it more precisely by equivalently adding fractional terms, fractional Chern-Simons term, to cancel the offending contact terms, and when we do that, everything is nice and superconformal. We can go to the sphere, find real answers as we want, but we pay a price, and the price is that the answers are non-invariant under all gauge transformations, or the extension of the fields to 4 dimensions. So here we see another aspect of this anomaly I mentioned. It's not just a clash between superconformal invariance and full gauge invariance. In this case, it's a clash between full gauge invariance and unitarity, which tells you which one you should sacrifice in a more obvious way. You should really sacrifice the invariance under large gauge transformations. So this brings me to the topic of F maximization. Now that we understand the phase of the partition function, we know exactly what we should do. In order not to be confused by the phase, we sacrifice invariant under large gauge transformations. We add the appropriate fractional Chern-Simons term to fix the problem. Now we have an honest-to-God conformal field theory. We can easily bring it to the sphere. And now we can use everything that appears in the standard conformal field theory books. Various properties of conformal field theory can be used without any problem. So the first thing we can do, okay, so that's what we do. We set the imaginary part of F to 0, and this also shifts the real part of F. So we add these terms, and now we can use standard things. And the first thing we use is the fact that in a conformal field theory, the one-point function must vanish. I should emphasize again, I forgot to say that this parameter T appears as the imaginary part of a background field associated with the U1 symmetry, and it represents the mixture between various flavor symmetries and the R symmetry, and that by this mixture determines the R symmetry in the superconformal multiplet in the infrared. So our goal is to find the value of T. Equivalently, finding the value of T is the same as finding the correct U1R symmetry in the superconformal multiplet in the infrared. And by doing that, we can find the dimensions of all chiral operators. So this is clearly an interesting thing to do. So this is this parameter T. And now we use the fact that the one-point function on the sphere vanishes. This just follows from conformal invariance. And since it vanishes, the free energy, or in this case it's the real part of the free energy, is at a stationary point. So F is extremized. This result was first conjectured by Jefferies, and now we see it follows from conformal invariance in a way somewhat anticipated by Jefferies, but now it's much more precise because we don't have all these phases around to confuse us. Second, we can consider the second derivative with respect to t. This is associated with the two-point function. Actually, the two-point function is at separated points. And now we use again positivity. Positivity is the statement that the two-point function at separated points is positive in the right units. This again follows from unitarity. Since our theory is now perfectly unitary, we can use that. And this tells us, if we trace all the i's and minus signs, that the second derivative of the real part of f must be negative. This means that f is at a maximum. This result was conjectured based on a few examples by Jefferies, Klebanov, Pufo, and Safdie, and now we see that it follows trivially from using standard field theory, conformal field theory, once we fix this problem with unitarity. And there's a throwaway comment here that f maximization is closely related to the F theorem, which unfortunately is not represented well enough in this conference. The next topic is another application of these ideas, is for the test of dualities. So there are many examples of dual pairs, conjectured dual pairs in 3 dimensions. These are 2 different theories which flow to the same infrared fixed point. More precisely, they are conjectured to flow to the same infrared fixed point. One problem with such dualities in 3 dimensions is there are very few diagnostics of the dualities. In 4 dimensions, we use the 't Hooft anomaly matching condition as a very powerful constraint, but in 3 dimensions, we don't have an analog of that. So now I'll present an analog of that in 3 dimensions using the discussion I had so far. So during the last year or 2, these dualities were tested by computing the S3 or the S2 cross S1 partition functions of 2 dual theories. This was done by these people and many others, and the results almost agree. So computing the electric theory, you're computing the magnetic theory, you get a horrible complicated function. This is an elliptic hypergeometric function. So you get such a function on the electric side, such a function on the magnetic side. Miraculously, they agree, but there is a prefactor which does not agree. So our goal now is to fix the prefactor. And there are 3 different elements in fixing the prefactor. First of all, we argue that the prefactor can be fixed by adding appropriate Chern-Simons terms. This restricts the functional form. I'll soon give an example. This restricts the functional form. The prefactor comes from adding these Chern-Simons term. The second restriction is that the coefficient of this Chern-Simons term must be quantized because it's part of the definition of the theory. We use the freedom we have in shifting the theory by such background field Chern-Simons terms with integer coefficients. We use this freedom, so we say that not only is the functional form dictated, but the coefficient has to be quantized. And finally, we can compute this integer. We can compute this integer if we have 2 dual theories which flow to 2 other dual theories. Then at one loop, we can compute the accumulated Chern-Simons term. So this is a completely straightforward calculation, a bit reminiscent of the 't Hooft anomaly matching condition. And now we can take all this information and try to compute the correction factor in this partition function. So here is an example. This is the Givon-Kutasov duality. They studied UN gauge theories, level K, Chern-Simons level K, with NF flavors. And we do one loop, and we find the correction factor. The correction factor is completely predicted. There are no free parameters to adjust here. M is a real mass for the flavors, and C is an Fi parameter. Notice that this term, we are really interested in e to the minus f. So the first 2 terms are a phase. Many people say, oh, it works up to a phase. But I emphasize that the answer is not just a phase. There is a linear term which is not a phase. So the correction factor is not just a phase, is a complex number. And now we had, just working in flat space, flat R3, we compute what the correction factor should be, and this is the answer. And with these 2 and with this correction factor, the two partition functions match. So what does this match tell us? It tells us that, first of all, it's a non-trivial test of the dualities, of course. It didn't have to work, and it works. And it's also a non-trivial test of our understanding of these contact terms, how to compute them, when they should be quantized, and so forth. And since all of us want to go to lunch, let me wrap up rapidly. In conclusion, contact terms are usually arbitrary. Chern-Simons contact terms are a little bit different. The integer part is arbitrary, but the fractional part is physical. The natural way to describe them is in terms of writing background fields, background gauge fields, and background gravity fields. We notice that in supersymmetric theories, some Chern-Simons terms are not superconformal. This is the anomaly I emphasized, which had important consequences when we studied the theory on the sphere. In order to preserve supersymmetry on curved space, we should turn on various supergravity background fields. I discussed that. And the non-conformal Chern-Simons terms lead to a phase of the partition function, which many people were confused by, but now we see very clearly where it comes from, which can be interpreted as violation of unitality, even for conformal theories. If we add counterterms in order to fix this phase, we see a proof of F maximization, which is actually quite straightforward. And as a bonus, we got an analog of a 't Hooft anomaly matching condition in 3 dimensions, and of course it works. So I'll stop and thank you here.
Questions?
Are there analogs of these contact terms in 5D superconformal theories? Have you thought about that?
Excellent question. I assume the answer is yes. I don't see why not. And I think it's worth exploring. There's only one, yeah, I'll leave it as that. But you see, you need a non-trivial fixed point. If the theory is free, then all these contact terms are basically quantized. It might be half integers if you have fermions. So it's not that exciting. It's much more exciting when the theory is interacting in the infrared. Yeah. But we have plenty of examples in 5 dimensions that you, among others, worked on of superconformal field theories in 5 dimensions, and for all I know, they have such contact terms.